All right, so what do we have? We have a pump. Again, this is an example for operation of cylinders. They're connected in this problem in series. We did couple in parallel in class. So this one, this specific one, it's very similar to what we did before, uh, but we only had two. Here, I'm just increasing the number to three, but it should be the same concept. We have three cylinders. The pump is actually supplying the first cylinder, which pushes a load of 1600 and then pounds. The back of cylinder one is connected to the supply of cylinder two. And then this piston pushes this time 1300 pounds. And then the load on the third one is 3200 pounds. And the back of two, as you can see, it's going to cylinder three, and then cylinder three goes back to the tank. That's maybe a main difference between what we'll be doing here and what we did before. But also I'm adding the pressure drop in the lines that you see there. So you have 1, 2, 2, 3, so on. Also in the DCV, we're gonna, let's see, 10 all the way to the 10. Okay, so this one that you see here only when we're going from the pump to cylinder one, 3 to 4. We'll take it as 7. And then in the way back, so we don't have, but it could be 7 in both ways. And then I have to split the lines and give you the pressure drop in the lines only. And that's when we look from point 10 all the way to the tank. It includes the tank, the lines, and the pressure drop in the DCV. Okay, so what do we have? We have the pump. It's supplying a flow rate of 15 gallons per minute. This time we don't have information about the pressure relief valve. If you recall, sometimes you might, when you're connecting, but that's probably when you are designing those, so to decide which one the pump should supply first. Should it go to cylinder one, then cylinder three, then two, or 1, 2, 3, or 3, 1, 2, 3, 2, 1. So it's going to change the supply pressure that goes into the first cylinder, and that can affect the PRV that you have. That's why we don't have a set pressure here. Usually, if you're designing, I would design it. I would calculate the needed pressure for the whole system and find the lines and select a PRV to protect the lines from bursting against any big pressure. A big note here, the tank is also open to the atmospheric pressure. If not, then we will have to add, if it's, let's say it was pressurized, something like this, and for some reason it's pressurized, then we have to add this pressure to my back pressure when we do cylinder number 3, which we're gonna actually do just right now. To simplify things on us, we do have the diameters, but also I calculated the areas here. It's not always you're gonna have those. So we have for each cylinder, we have the diameter of the piston and the diameter of the rod. That's probably what you will be given. And you will have to calculate the piston area, the rod area, and then find the annulus area, which is needed for the retract area, or when you do the retract area and pressure. The no load testing information for each cylinder is given here. That's cylinder 1, 2, and 3. This is the cap side, and this is the retract or the rod end side. So one from the front, and the other is from the back. So just as a reminder, what's the no load testing? It's when uh, you will take each cylinder by itself with no load, and you will put it on a testing machine, and you would check the pressure before and after, and then you start running this. So you would have the two pressures during no load testing. We did a lab related to this concept in previous courses, and that's what we have here. We have the P cap side and P on the rod side. So What that reveals, it's giving you the pressure on both sides of the piston. So the difference will be used when you calculate the force. The difference between the two forces will give you the frictional force between the piston and the cylinder side. Okay. So we will need to do that if they don't ask you to find the friction. I believe they do ask you to find. If not, you can't start because ultimately they would be asking about the pump requirement, which is the pressure and maybe the power. Yeah, find the power, and then they give us some efficiency information for that pump. So the question could simply be find the power needed by the pump, or even the shaft torque and power needed in order to drive that pump. So to do that, I will need to find the pressure. I will need to know the flow rate, which we have, and then I would also need to find. First, I will need to find the friction in order for me to find the pressure needed. So even if they don't ask you to find the friction, you would still need to find it in these cases. Okay. So in the first part, when we do the friction, when we will be calculating the friction loss, I don't need to include any of these three loads, W1, W2, and W3. That's part of how we find the supply pressure for each cylinder. In this case, the supply pressure that would supply the three cylinders because they are connected in series. And before we start, just as a reminder, we said when we have those, they are in series, I would start from the very last cylinder or the closest cylinder to the tank because the bag goes to the tank. So that's where we would go and calculate the supply pressure coming here. And this would serve as the back pressure plus the pressure drop in the lines. All right, let's go ahead and get started with the frictional losses. We have all the information on the next slide. So that's where we're going to start. Cylinder one. So in general, what we have, you have P cap, so P of the cap side times the area of the piston. They're all the same. The supply is coming, the supply is here, and then this would go back to the tank. So the cap side area times P cap, the back or the rod side area, the annulus area, times the rod side end pressure. So P cap, A cap, minus P, if you want retract, or P rod times the retract area or the annulus area that we have here, minus the frictional loss equals zero, or the difference between the two pressures. That's F1, F2, F on this side, F on the other side. That's F on the cap side. That's F retract. So this one is P cap, A cap. This one is F retract, P retract, A retract. So the difference between the two would give us the frictional loss for each cylinder. So FF for cylinder one, what do we have? We have 70 psi, pound per square inch. The area, A piston or A cap, it's 50.2. Inch square minus the retract, so 10 psi, pound per square inch, into the retract, not the rod. So 43.2 inch square. So that would be in pound force. So this would be 3,086.585 pounds. Okay. Similarly, we'll do friction for and cylinder two. So it's P cap, this time it's 50 psi times 28.274 minus 20, the retract pressure, into 25.132. So that's the retract area. This time will be 911.06 pounds. Again, whether you have these connected in series or parallel, you would need to do this, and it's not going to affect the answers. That's the retract pressure. Sorry, that's the frictional loss on each cylinder when it's on the testing station by itself. So it's not connected in parallel or in series. So frictional force in cylinder 3 would be the cap pressure times the cap area of the piston minus 25, the retract or the rod side pressure times 31.418, which is the retract pressure for the last cylinder, and that will be 3,447.9. Okay, this equation is not going to change regardless. So you have in series, in parallel, even if one of the cylinders is connected to a pressurized tank, it's running another system. Those are the frictional properties for each piston when it's on the testing station. Okay, now we're going to go to the system. So now I will start analyzing the system. In part B, they're asking us to find the pump supply pressure in PSI to raise these three loads at the same instant. Then they'll probably, let's see, they're not going to ask us to make sure that they're all running at the same speed, but we need to make sure that they all start at the same time, and that's where I'm going to need the pressure needed for the first cylinder, and then we can move back to the pump. Okay. So as I've said, we will start from the very last cylinder because that's the one that connects to the tank. If I have here then any pressure, then I will need to add it to the retract pressure that we have from the no load testing. And we're going to see that as we move to the two other cylinders, cylinder 1 and 2. Because cylinder 3, it's not affected, and that's the information I have, and that's why we start with this one. But in this case, I do have a pressure drop which is, let's see, 25. So let's put the equation first. In general, similar to what we had there, and don't forget the load. So we have now P supply for each cylinder. It's all the same, this equation. You have like this, and you have the supply coming here, and that's the back going back to the tank. So here we have the supply pressure here, which we call P cap, but since it's supplying the load, because I have W here, or if you want to call it F load, excuse me. So F on the cap side, P supply times the cap side of the piston, that has to be equal to P retract on the back side, or P rod, I should call it, similar to that one. But since we will have to add any pressure drop, the tank pressure drop, so on and so on, I will need to, I will just keep it P retract so that I can differentiate between this one and the pressure that we'll be calculating. Plus the frictional force plus F load. Okay, so do you see the difference between the two equations? When you don't have a load on the piston, then this would simply be the cap pressure from the no load testing, and that's what we use to find the frictional force. And then we're going to plug that frictional force, put the flow, and then calculate the supply pressure. And then we would move back to the cylinder that comes before this. So P supply 3, you can also take this, divide it by that, and have a general equation for also P supply for cylinder 3 as 1 over A cap 3. I'll just, since I have the equation, I plug the information directly. What's A cap 3? It's 38.485. Okay, that's A cap 3. And then I'm going to put this equation down here with the numbers. What do we have? I have 25. This should be 35. Okay, it didn't add it on my, so I'll just say neglect this because I didn't add that number. Let me double check my calculation. All right. So 25, let's assume it's neglected, any pressure drop here, and we'll make a note after. So 25 times the retract 31.4 plus the friction for cylinder 3, we found it 3447, 3447.9 plus the load on cylinder 3, 3200. That's why I said if you can print uh, this information before, so you don't have to keep going back and forth. I have it here. Now we have to make a note here. This 25 should be the retract pressure, the rod side from the no load testing, plus delta P from 0.10 all the way to the tank, plus P for the tank. Does it make sense? Because now I'm adding pressure into my system, so I have to add these to that point. I don't know how I skipped that on my notes. Let me just do a quick calculation. Also, if you want to check it. Yeah. And the reason I don't want to fix that, it's an easy fix to add since we don't have pressure in the tank, I don't have any pressure here, it's atmospheric. So I will just need to add 20 to my pressure, the 25, and this would be 45. But whatever answer we're going to get for this is going to affect the answer for the second, the answer for the first cylinder. And that's why I'm just saying neglect over there, and we're going to just put a note here. Okay, I got here 193.15 psi. That's the supply pressure needed for cylinder 3. So now that pressure is actually coming from cylinder 2. So now this becomes the retract pressure, plus, of course, the pressure drop in the line. Okay, so then P retract two as P supply 3 plus delta P for that line. What's that line? It's 8 to 9. Okay, so it's 193.15 plus the pressure drop in this line. This line here, which is 5 psi. So I will take that, add it to the 193, and be careful. Sometimes you're moving forward, sometimes you're moving back. So if we move back, then the pressure upstream should be higher. So I will need to add the pressure. If I'm moving forward, like if you have a pedal and you have the pump pressure, you're trying to find the supply pressure, so you're moving forward, then you will need to remove that 5 psi from the upstream pressure. In this case, my upstream is PR2. So I will need, so kind of like you will take the 5 to the other side to find this pressure and then move forward. Okay, and don't forget the retract pressure from the no load testing, plus 20. Usually, if we don't have the pressure drop, I would just say 193 plus 20. So it's the supply plus the retract pressure from the no load testing, and that's what this resistance of the oil in the back is if we don't have anything connected to that cylinder from the back. Okay, so I will take that value and plug it plus 25, 218.15 psi. So now we will do the same equation. So P supply 2 is 1 over A cap 2, the 28.274. There's a dot here. Can't put it down there. All right, we'll take the 218. That's my Peter track 2. Okay. Aero track 2 is 25.13. One 32 plus the frictional loss, which is 911.06. And then what's the load? 1,300 pounds on cylinder 2. Okay. If we do this, it would give me 272.11 psi or 109 psi. Okay, because this answer is going to affect this answer, which would be here, and it would affect the answer. So I will have to recalculate everything, which I should. So, okay. So now that supply pressure is going into cylinder 1. So now we will do similarly. That's why I said whether you do 2 or 3 or 10, it's the same process. It's automated if you have these. If you have this information, the areas, everything, the no load testing information, if you can program it, then you can put any number of cylinders in series and you can put this equation. So it would recalculate the supply. That would be the retract pressure for the cylinder that's before, in this case, the prayer one. So cylinder 1. So we have P retract 1 as P supply 2 plus delta P in the lines plus P retract 1. So what do we have? I have P supply 2, it's the 272. We just calculated that. Plus delta P in the lines, which is 6, 7. So 6 to 7. And P retract 1 is 10. So I'll take that 10. Let's check what's 6, 7. It's 5 as well. So here 5 psi plus 10. So that would be here. So now I'm good to find P supply 1. It's 1 over A cap 1. What's A cap 1? 50, I believe. Yeah, 50.2655. B retract 1 to 87.11. A retract 1 is 43.2 plus the load and friction forces, 1600. Okay, the frictional loss is 3086.585, and the load is 1600. So we have those correct. All right, I will get around I will get 339.99 psi. So I'll just take it 340 psi. I already rounded some numbers up and down, so I can make that estimation with good accuracy. It's nothing, it's almost the same. Okay, so now that's my pressure or the pressure needed to operate those three cylinders at the same instant. So once we hit that pressure at 0.5, okay, that's the supply pressure for cylinder one. Usually, the previous examples we didn't have, or we said neglect any pressure drop in the lines. Did they say neglect pressure? Yes, neglect the weight of the piston and rod. Actually, I'm looking into the minor loss. They didn't say that. They just gave us the pressure drop inside the connecting line. So probably that includes losses here and the elbows and so on. If not, then probably they should say neglect the pressure drop in the fittings, and those are frictional losses in the lines. Why I'm saying that? Because now I have P5, that's the pressure needed to push cylinder one, for it to push cylinder two and three and push the oil back to the tank. But that's not the pump pressure. They're asking us to find the pump requirements, which is the pressure and then the power needed. So I will need to go back from P5 all the way to the pump. So P for the pump is P supply 1 plus delta P in the lines. What are the lines that we have? I have 5 to 4, because I'm going backwards. Here, 4, 5, or 5 to 4, and then 3, 2, and 2, 1, and of course the DCV. So if you want to make it a different color. Okay, so I have 2, 3, 7, 7. 340 plus 2 plus 3, I believe they are like that. 1, 2 is 2, 2, 3 is 3, and 7, and 7. So 10 and 9, that's 19, so 359 psi. So that's how much pressure I'm going to need at the pump in order for it to push the oil or to start all three cylinders together. All right, next we need to find the power needed to drive the pump if it has a volumetric and mechanical efficiencies of 75% and 81% respectively. All right, I need to know now the power needed to drive that pump. I have the pressure. It's 359 psi, and the flow rate Q dot, or just Q, it's 15 GPM. That's the information I have. Usually we would say PQ over 1714. That's actually what we call the hydraulic horsepower, and that's the output from the pump. That's how much the pump is delivering in terms of power. So it's P Q over 1714. This would give me the what we call the hydraulic horsepower. That's not what they're asking us to find. They're asking you to find the power needed to drive the pump. So kind of like they're asking for the power right here, the mechanical power on the shaft, because also I can go back from here all the way to the electric power needed. So I need to know more information about the windings, the losses in the lines, and so on. So they should give you the electrical loss. We can add that after we're done. But since I have now those two efficiencies, I can find the input power. Simply the overall efficiency is the mechanical efficiency times the volumetric efficiency, and that's equal to the out power. So it's the hydraulic horsepower out divided by the uh, power and the HP, and since this would be in horsepower. So we will get H, that's the horsepower needed, N, it's the pressure, the pump, delta P times Q for the pump, divided by 1714, all that divided by the overall efficiency, which is 0.81 times 0.75. And of course, since we will focus on this actually on the next in the next problem. This flow rate has to be the actual because we're using uh, the total efficiency, so it has to be the actual flow rate. If you're using, because I can also use the mechanical efficiency, but that has the flow rate has to be the theoretical flow rate, so it doesn't have any volumetric losses in it. So we'll plug these numbers here and we will get the horsepower N should be around 5.17. Of course, P in PSI, Q in GPM, that's what we have. Divide by 1714 times 0.81. 5.17 horsepower. Again, that's only the mechanical power needed to run the pump. If we need the electric power needed, then I need to know probably what we call the electric efficiency. And then we would add it to my efficiency. So you will be dividing by, again, we're moving back from the output to here. There are losses, so I should have more power here to overcome the losses and give you the whatever this answer is, divided by 1714. And then that's the 517. I'm now here. I need to know how much power I have. So here we have electrical losses. So we divide that answer, the 517, by the electrical efficiency to know Pn at this end. Okay. We won't be doing this. We're more focused on the hydraulic part, so we will only be dealing with the mechanical and volumetric efficiency. All right. The next part, we need to find the flow rate feeding cylinder 3, which is the last one. Remember, the 15 gallons, you might say, oh, I have 15, so it has to be 15. No, that's 15 gallons per minute coming here, and it's feeding cylinder 1. But how much is actually feeding cylinder 3? It's different. Okay. So cylinder 1, the back oil is moving at the same speed as the speed of the oil in front of the piston in cylinder 1. But this oil now leaves with this speed and it feeds this cylinder. So now that speed, V1 times the cap area of cylinder 2 will be the speed of piston 2. We can find then the speed of the oil in the back of cylinder 2, and that's the speed that's the flow that goes into cylinder 3, and so on. Let's see those in terms of numbers. I mean equations. So I have V1 in cylinder 1, that's Q1 divide by A cap 1. Okay, what's Q1? That's the flow rate that goes into the first cylinder. So that's 15 gallons per minute. I'm going to multiply that because I need to have it either in inch per second or feet per second. I'm not going to leave it in gallons per minute. The area is in inch square, so I will need to convert that into uh, cubic inch. 1 gallon is 231 cubic inch. And of course, I have the per minute, gallons per minute, so I'll need to divide by 60. So 231 over 60, this actually a common conversion when GPM is 3.85. If you divide 231 by 60, you should get 3.85 cubic inch per second. So now I have cubic inch per second per gallon, per GPM, and here 15 GPM, so they cancel. And I have cubic inch per second. And I have A cap 1, that was the 50.2655 square inch. That's coming from this table, 50.2655. So that would be 1.149 cubic inch, inch per second. Now that's the oil in the backside of the cylinder. Sorry, that's the speed for all. This oil, the piston, and the oil right here. If this is incompressible, or even if it's air within acceptable range of compressibility, then we can say it's incompressible. So all of them, they're gonna move at the same speed, V1. So now what's the flow rate that leaves cylinder 1? It's the oil right here. So it's the same speed. So Q2, the one that goes into cylinder 2, it's the back flow rate in cylinder 1. It's V1 times A retract 1. Okay, so it's 1.149 inch per second times the back area of cylinder 1, the annulus, not the rod, which is the 43.2. That's inch square, so I should get now Q2, it's 49.64 cubic inch per second. So we'll repeat now this, but for cylinder 2. So now V2 is Q2 over A cap 2. So it's 49.64 cubic inch per second, divided by A cap 2, 28.274. Inch squared, and that would be 1.755 inch per second. And the same way, now I can calculate Q3, Q that feeds 3. It's the same speed here, but times the retract area for piston 2, which is 25.1532. So Q3, they ask for the flow rate only, and then they're going to ask for the velocity. So we have space here. I can Q3, it's V2 times A retract for cylinder 2, so it's 1.755. A retract 2, as we said, 25.132, and that would give me 44.117 cubic inch per second. If you need it in gallons per minute, just for comparison or for whatever reason, we will, I can use this conversion here. So Q3 is 44.117 divided by 3.85. That would be 11.46 gallons per minute. Usually the question would directly ask you to find the velocity in a specific cylinder. So they won't ask for the flow rate, but that's the process, especially for series. In parallel, we don't have this process. It's only the flow rate, but I need to know how it splits between the two cylinders. Because you have the pump coming here and it provides multiple cylinders. So I need to know how much is coming. We will divide that flow, the partial flow in that branch that comes into that specific cylinder. We'll divide it by the cap area or the area in general that supplies that piston, and that's the velocity in that piston. But when it's series, I will need to go from the pump. We said when we do pressure, we move backwards from the tank back all the way to the pump. When we're doing flow, we start from the pump side and then we move forward towards the tank to find the velocity because I'll need to find the supply flow, which we have it. So I need to find V for the first cylinder times the area of track 2 of 1. It gives me my Q2, and then I can find V2, then find Q3. From Q3, I can then find V3. Of course, I'm gonna just stick to this because again, the area is this is a cap 3. It's an inch square, so this one would be 44.117 divided by 38.4. Let me just double check. Yeah, 38.485 cubic inch per second, inch squared. So again, I'm gonna have the answer in inch per second. Okay.